Today, I'm going to show you how to calculate permeability from production logs. Here we have a production logging interpretation showing a number of very clear inflows and a permeability log. This log was obtained from wireline logs and core data. And we know that sometimes the effective permeability can be quite different to the prediction of these logs, especially in naturally refractory reservoirs or reservoirs with boggy porosity. So we are going to use dynamic data to compute the apparent permeability. For this, we are going to use the Darcy equation. Here you can see Darcy in cylindrical coordinates. And as mentioned, the permeability is unknown, is what we want to calculate. So from where are we going to obtain the other parameters? Well, let's see, the rates are the contributions, okay? These are the contributions calculated as a result of the production log interpretation. We have a number of fluid properties, in this case the volume factor and the viscosity, that are already in the production log interpretation as we define the PBT. Then we have the delta P, the PWF, is measured directly by the pressure sensor in the tool string. The P-bar, we are going to estimate the P-bar using the selective inflow performance technique. And then in the denominator, we have the skin, okay? So for the skin, ideally, we would need pressure transient analysis. And then we have the ratio of the external reservoir radius and the wellbore radius. This will typically be a value between 9 and 9.8, let's say, because RE is very large compared to RW. So when we take that natural logarithm, it results in a value around 9. And then finally, the thickness, okay, you can ask the petrophysicist, or we will also have certain layering as a result of the production log interpretation as we define the inflow zone. So ideally, we should use the inflow zones as an estimate of H. Okay, so let's see how we implement this in Emeraude. As mentioned, first we need to perform a selective inflow performance to obtain the average reservoir pressure. So we need to define a number of reservoir zones. I'm going to say that this upper perforation is one reservoir. And then the second one is also a single reservoir. And the three perforations here are part of the same reservoir. So for a selective inflow performance, we need a multi-rate PLT. This is PLs recorded at different rates. Here we have a low rate, also medium, and shut-in. The shut-in indicates cross flow. Okay, so we go to the special tab and look at the selective inflow performance, showing the PWF, so the pressure on the vertical axis, and the rates on the horizontal axis. Here we see the IPR for each of the reservoirs. As you might remember, the intersect with the y-axis shows the average reservoir pressure. If we look at show results, we can see the p-average. Okay, this is the input that we were looking for, and the productivity index. Okay, so from where these two parameters come from? Well, they come from the same equation that we were looking before, Darcy equation. If we group all the reservoir properties, PVT properties, and near wellbore damage, we obtain what is called the productivity index. And this delta P that we see here is what we call the drawdown. So the productivity index in the IPR curve is the inverse of the slope, and the p-bar, as mentioned, is the intersect with the y-axis. Okay, so let's proceed with the permeability calculations. The permeability from production logs is called A-perm, okay? So I click here on A-perm, and we can see basically for each inflow the all the parameters necessary to solve the Darcy equation. So the P average, this is from the selective inflow performance. PWF, this is the measured pressure. External reservoir radius, I'm going to use a typical value here, but of course you can decide this with your reservoir engineers. The RW is, in this case, is 4.25. This is a 7-inch casing, so 4.25. Okay, and then the skin, as mentioned, we need a pressure transient analysis. I'm going to start with a skin of 0. And you will see that as soon as I enter 0, here in these two columns, the permeability and the permeability thickness products are being computed, okay? So this means that we have all the necessary inputs to solve the Darcy equation. If you see here, there is a well test KH. So this method, the APER method, works best when we combine it with the conventional pressure transient analysis, right? First, because we need a value for the skin, and second, because from the conventional PTA, we will obtain a commingled KH. And let's say, for example, that this commingled KH was 70,000 millidarcy per feet, and we can compare this with the cumulative KH from PLT. We can obtain a normalization factor here. So this tells us that if we were to multiply the cumulative KH from PLT by this value, we would be at the same KH as the commingled from PTA. So that's it. I'm going to click OK. And here we can see the results. So let me just remove some of this first. So the results can be seen, for example, in this track, where we show the original permeability from the log and the permeability from production logs as blue lines. Okay, so we can see that the estimated permeability is larger than the one from logs. Then we can see a boost factor. This shows basically the multiplier that we should apply to go from the original log permeability to the A-perm. And then finally, the log permeability, including the dynamic data from the A-perm. Okay? So this technique is very powerful, especially as mentioned in reservoirs like naturally fractured carbonates or in vaggy porosity, where the core data is typically not very reliable, and also is a really good opportunity for you to squeeze the production logging data and extract more value from your operations. Okay, I hope this was helpful, and see you in the next video.